let's look at trigonometric function modeling. We can use trigonometric functions to model real-world phenomena. Look at the functions given to you and answer the questions given about the function models. So in this handout, we have two scenarios, two real-world phenomenon where we have the orbit of Mars around the sun, and in the other problem, we look at the average temperatures in Seoul, South Korea. So to start this problem here, looking at Mars, the handout tells us that m of t models the distance in millions of kilometers from Mars to the sun t days after it's at its furthest point. Here, t is entered in radians. So we know we're in radian mode for our function. And we have this function that tells us 21 times cosine of 2 pi over 687t plus 228 will model the distance of Mars from the sun. And I have a image here that'll help you visualize what it looks like for Mars to orbit the sun. It's a very simple diagram, nothing fancy. Let's go ahead and look at the first question here. It says, how many days does it take for Mars to return to its furthest point from the sun after passing it? What the model tells us is that, because it says t days after it's at its furthest point, so at t equals 0, Mars is at its furthest point. So just to use my little diagram here, this position here is when t equals 0, because it's at its furthest point in the orbit, and then it's going to orbit this way around the sun. So how many days does it take for Mars to return to its furthest point from the sun after passing it? Basically, they're asking us, after t equals 0, how many days does it take for it to revolve completely around the sun? So when it finally returns back to this original point. In periodic functions, such as sine and cosine, this is known as the period. So since it's a cosine function, we're looking for the period of this cosine function, right? So we're looking for the period. Well, period has a formula, which in radians, we call that 2 pi over the frequency of the function, frequency of the periodic function. Well, let's recall what the frequency of a periodic function is. When you have sine or cosine, the expression of the angle in the cosine or sine function, so right in here, frequency is the coefficient of your variable. This expression right here, 2 pi over 687, that would be our frequency. It looks kind of rough, but what we're going to have to do is evaluate this expression. We're going to take 2 pi and divide by 2 pi over 687. Now, recall that when you divide by a fraction, you're actually multiplying by its reciprocal. This would be equivalent to this product. We could do 2 pi times the reciprocal of 2 pi over 687, right? The reciprocal of this expression here. So that'd be 687 over 2 pi. We get a very nice period. The 2 pi factors cancel with, right, and leave behind a 1. And 1 times 687 is 687. And the unit of t in the model is days. So according to number 1, the way we would answer this is it takes 687 days for Mars to return back to that point when it's at the furthest from the sun. So if I were to add that to this, we could also add that t equals 687 is also when Mars is at that position. Okay, number 2, what is the closest distance from Mars to the sun based on the function model? So here's where it helps to know a little bit more about sine and cosine. So sine and cosine have features known as maximum, minimum, and a midline. And why that's useful to connect all three is that if you know the midline, then you should be able to figure out its maximum and minimum based on something called the amplitude of the function. Okay, so we've already determined that the 2 pi over 687 is something known as the frequency of the function. Well, what about the 21 and the 228? In a cosine function or sine function, the positive value that's multiplying the cosine function right here, the 21, that's also known as the amplitude of the function. And just to be clear, it is a positive value. You'll see some modeling functions or cosine and sine functions that have a negative. The negative is not part of the amplitude. The negative is part of the fact that you would have a vertical reflection of the function, which we're not really focusing on right now. But the amplitude of its in of itself is this positive 21 in this case. And this 228 value that's adding the function, In function transformations, this is just our vertical shift, but we also call this the midline when we're specifically addressing periodic functions. It's the midline value of the function. In order to determine the maximum and the minimum of a periodic function like sine or cosine, you would have to know your midline value, and your maximum would be the midline plus your amplitude, and the minimum would be your midline minus your amplitude. So to correctly answer number 2, it says, what is the closest distance? This would be our minimum. It would be the minimum of our distance function because we're modeling distance from the sun. We would take our midline value and subtract the amplitude, which in this case would be 228 minus 21. So this would be 207 million kilometers, right? Because our unit is in millions of km, right? Millions of kilometers. Now, to help this be a little more straightforward, a little more clear, we can look at a graph of this function. All right, so let me go ahead and type it in. We have m of t equals 21 cosine of 2 pi. Remember, for pi, you could just type pi, 687 t plus 228. As soon as I'm done typing the function, you'll notice we don't see the function on screen. And that's because this function has a very high, right, a very high up the y-axis midline. So if I scroll out and like move around with my mouse, I'll eventually find that, oh, okay, we finally have the function. It's up here somewhere. Something else I can mess with is making this darker, more pronounced by clicking this capital A thing. It's not a bad viewport. I will go ahead and decrease this a little bit. Let's go to 300. And what's really useful is to graph the actual midline of the function. So if you remember here, our midline was 228 value. So I'm going to graph an extra function to help me visualize things. Y equals 228. Now that's a constant function, right? 228. So it should be like a perfectly horizontal line. And this will help us see where our function kind of like oscillates, right? So we have some of the function being above that midline and sometimes it's below it. And that helps us recognize the periodic nature of this function. So what you'll notice here, just to kind of verify something, is you'll see that when this function starts here at 0,249, that's when Mars first passed the furthest point from the sun. And when you wait 687 days, you get the same value because it's finally reaching the furthest point from the sun. So number 2 was asking us, what was the minimum? So we answered it's the midline minus the amplitude. And we can actually see here that if I click on this point here, we have 207, which is the same answer we got, because if you visualize from the midline, you're either 21 million kilometers above the midline, which is why our maximum is 249, according to the graph, and our minimum would be 21 million kilometers below the midline value of 228, which is 207. So just thought it'd be nice if we used a graphical representation to kind of help us visualize what we're even answering here, right? So what this graph is showing us is the representation of the distance from Mars and the sun over time, over a certain number of days, t. Okay, continuing on, number 3 asked us, what is the greatest distance from Mars to the sun? Well, the graph I just showed us illustrated this, but just to kind of keep in line with how we answered number 2, it would be, instead of our midline minus our amplitude, right, to find the minimum values, we're trying to find the maximum now, right? This would be the maximum. So we're trying to find the maximum value. And our maximum value would be midline plus amplitude. And that would be 228 plus 21, which is 249 million kilometers. All right, number 4, calculate the distance from Mars to the sun 87 days after Mars passes its furthest point from the sun. So now we have to just explicitly use the function, right? The function is a model where we plug in t for a number of days, and it'll just give us the distance of Mars from the sun. What I like to do to kind of help me is I like writing my function, and I'll rewrite it, 21 times cosine of 2 pi over 687, and it's times t, right? So I'll leave like a blank for t, and then plus 228. I like to kind of rewrite my function, and then I'm going to leave blanks for where I know I'm going to substitute a value. So since I'm finding m of t, where t is 87 days, we're finding something known as m of 87, right? According to the function, what happens after 87 days, and 87 would also be my blank where t was, right? That's where t was. This value right here, 87, is where I'm replacing t. How are we going to figure this out? Well, at this point, this is where you would definitely just rely on a calculator, right? And you can just hop back into Desmos. And there's nothing wrong with using a calculator for a lot of these kinds of function modeling, because no one would know the evaluation of this function without the help of something like a calculator, especially for values like 87 times 2 pi over 687. Of course, we can use a calculator. According to my calculator, all right, so I'm going to go ahead and type it in. 21 cosine of 2 pi over 687 times my 87 days plus 228. And you can see there, according to my calculations on Desmos. Now, make sure, usually the default is radian, but remember it told us that t is in radian, but we are plugging in radians, not degrees. So there's my result. 21 times cosine of all that plus 228 is 242.6956, etc. We'll just round to the nearest million. So we'll just say 242.7, but the 0.7 would round us up to the next million. So let's just say 243 million. 243 million kilometers. Okay, number 5 asks us to calculate the distance from Mars to the Sun, 226 days. So you're just explicitly using the function once more. So I'll leave that for you to do. And lastly, we'll look at number 6 for this model with Mars and the Sun. How many days later does Mars first reach a distance of 220, oops, that meant to say million kilometers. Million kilometers from the Sun, right? Because our unit's in millions. Sketch a graph that helps you determine the answer. And of course, the hint is to use a graphing utility like Desmos. So if you want to use something like Desmos, that's totally cool in this scenario. So if you remember, just from my quick look at Desmos, the graph, our cosine graph looks something like this, right? And I graphed something called the midline. And the midline cuts directly through the function, right down the middle vertically. So that was y equals 228. That's our midline. What this is saying is, well, what about 220 kilometers? Similarly, what you can do, so if that purple line represents 228 million, what you can do, and I'll leave this as an exercise for you on Desmos, what if you graph the line 220? That would be a different horizontal line. That would be a little bit lower than this, right? So let's say it's down here somewhere. So what if you graphed y equals 220? Well, using Desmos or any other graphing utility, you can find where that horizontal line will intersect our cosine model, and would be here, right? And it asks for the first time, right? Because it does keep intersecting because it's periodic, so it'll keep intersecting 220. But this is the first time it intersects the cosine model, and therefore your point of intersection will be some x value, but we know that the distance is 220. Using Desmos or any other graphing tool, try to see if you can find what would be the intersecting x value, or actually, since our model is using t, I guess I should technically call it t, this would be your t. However many days it takes to get to 220 would be the resulting answer you're looking for. So I'll leave that as an exercise for you.